Okay, hey everybody. So this is part three, and I'm finding that it's a little bit easier for me to do shorter videos, and I think it may actually be a little bit easier for you too, because you can just find the thing you want to find right away. So I think I said in part one there's going to be like 4 parts, but now there might be like 6 parts. I don't know, we'll figure it out as we go. But this is going to be a short video just on how to set up the camera frame. So where we're at now is we're trying to calculate this camera transform that takes us from world space to camera space. World space is where triangles are in some native XYZ form. Again, I already referenced in part one of the video the example I did on Thursday in class where we picked an origin of the floor in the back left hand of the classroom, and then we specified the coordinates of the triangles that form the chalkboard from the basis vectors we defined of x, y, and z. And so those would be our world space triangles, and now we want to transform them into camera space, which is relative to a camera frame. And with camera space, the camera is at the origin, and the camera's orientation is looking down the z direction. And so there's 2 parts to this. One is to construct a camera frame, and that's what we're going to do in this video. And then after we construct a camera frame, then we can construct a matrix that transforms points from the Cartesian frame world space to the camera frame. And so this video is all going to be about how to construct a camera frame. And remember, a frame, this was in Thursday's lecture, is when you have 3 basis vectors and an origin. So, a camera, so here's a little bit of linear algebra we didn't get into on Thursday, which is a camera frame must be a basis, and so it needs to span our space. You need to be able to get to any point in our space through a linear combination of the basis vectors, and that means the members need to be linearly independent. This is the part we didn't talk about, and so I'll have a slide showing what it means to not be linearly independent. But linearly independent means that no basis vector, that's not good English, no basis vector can be represented via the other basis vectors. So we had this slide before where we looked at what happened when we were taking steps in D1 and D2, and then I said, what if we add D3? And so this would be an example of basis vectors that are not linearly independent, because you can form D1 out of steps of D2 and D3, or vice versa. It might involve negative values, it might involve fractional, but for any 2 of the basis vectors you can form the third, or for any 2, I shouldn't call them basis vectors, for any 2 of the vectors you can form the third. And so for our frame we want to have linearly independent vectors. Now I do want to say these, if you take just 2 like D2 and D3, these are linearly independent even though they're not perpendicular. And we're going to do something tricky as we set up the camera frames. We actually really would like them to be perpendicular. And so linearly independent doesn't mean perpendicular, but we're actually going to have them be perpendicular, which would definitely make them linearly independent. Okay, so again, to make a frame, we need to have, for our 3-dimensional space, we're going to need 3 basis vectors, u, v, and w, and an origin. And so some of this we can derive right away, that our origin is going to be where the camera is. And because it's right here in our notes, camera located at the origin, looking down minus z. And so right away, we can set our origin equal to the camera position, and we can set the w basis vector to be looking down minus z. Now, this is an arbitrary decision, right? We could have said it's looking down minus y, or looking down minus x, or looking down plus x, or whatever, but this is the convention, right? And so this is the convention of camera space, and we're following that convention. If we wanted it to be different, we could define the conventions differently, and the math would work out differently. But the math that we're going to have is for the matrices that we're going to define are for this specific set of conventions. So to do the camera frame, which is the goal of this video, we need 4 things: 3 basis vectors, u, v, w, and an origin. And so we've now done half right away, the origin and one of the three basis vectors. By the way, I set this to be the origin minus the focal point. Here's the origin. You could say the focal point's right there. If it was origin minus focal point, that would be pointing that direction, and that would be plus z, and we actually want to be looking at minus z. So that's why it's origin minus the focus, because origin minus focus would get z that way, and we want to be looking down minus z. I think I said that wrong. We want it to be origin minus focus because that would make plus z going that way, and we want to be looking down minus z. Okay, so now our challenge is to define u and v, and we're going to do that by using another one of the data members, specifically the up vector. We talked about the up vector in part 1 of the videos, and so the up vector defines the orientation of what is up. Remember, there was the picture of the up vector going from the top of my nose through my forehead. And as I turn my head, what I see is as up, the top of my image is based on that up vector. And so here's the rest of it. We're going to say that v is going to be the up vector. Now this is actually not going to be our final solution. V is the up vector. This is a temporary solution getting us on the path to the final solution. We're going to say v is the up vector, and then once we have v as the up vector, then we can set u as the cross product of up and w, O minus focus. And so you remember we talked about the cross product in video 2, and the cross product takes two vectors, in this case up and w, O minus focus, and it would find a new vector which is perpendicular to them both. And so, we'd like it to be, I already mentioned this, that u, v, and w, our three basis vectors, are all perpendicular to each other. And we're almost there because we know u is perpendicular to v, and we know that u is perpendicular to w, but we actually don't know that v is perpendicular to w. And so what that would look like would be, in fact, that's probably my next slide, is that our direction of view and our up vector may not be perpendicular. And so here it's saying, what if their dot product is not 0? And of course, if the dot product is the cosine of the angle between them, then if they were perpendicular, then it should be 0. So anyway, the point is we're going to do this trick where we start with this, the two that we know, up, and then u being up cross product with O minus focus, and we're going to keep u, which is perpendicular to them both, but when we set v, we're actually going to go and set it to be perpendicular to O minus focus, w, cross u. And so what that's going to do is we started with this vector, we took our up vector, we made our u vector, which would be coming out of the screen, because that's the vector that's perpendicular to them both. And then we're going to take the vector u that we created and go to this original O minus focus vector and take the cross product of those, and then it will make some new vector v, which is going to go straight up because it will be perpendicular to O minus focus. And then we're going to have three basis vectors u, v, w that are all perpendicular to each other. So this is the camera frame, and hopefully it's clear how to derive these from the data members. Focus, the O is the position, right? Origin is the camera position. And so hopefully it's clear how to derive these from the data members in the camera class. And so now we have our camera frame, and that's going to allow us to go to the next step, which is to calculate the camera transform, which is a matrix that transforms points from the Cartesian frame to the camera frame. So that will be the subject of the next video.